Okay, we talked about the damped. Harmonic oscillator, and then we say, hey, this is damped. Meanwhile, this one actually corresponds to electrical circuits. These two systems are equivalent, so you can actually use the study in one system to study the other one, which is fantastic. So, and we were talking about testing airplanes. You, instead of building an airplane and destroy it, what you can do is build an electric circuit and destroy it, which is way cheaper. All right. That's what we had for harmonic oscillator. Now we were talking about 2.4. Additional analytical method for special systems. Okay. Let's give us several information. Number one, for any system, maybe it's difficult to find the analytical method, which means solving the thing by using, for example, integrating factors or any mathematical ways. Okay. But this thing does work for some special ones. The first one is called completely decoupled system. Which is something look like this. Negative x. Okay. Clearly, this is a system. You have two things, x and y. What's special about this system? If you think about it, you realize what happens with x has only something to do with x. And what happens with the tangent rate of y has only something to do with y. In other words, x, y do not interact. Or in another word, if you completely delete this equation, it doesn't change the differential equation here. The solution still stays the same. So with this or with this, without this, we can solve it as if it's just one differential equation. Similar thing works for the second one. So solve one, which has nothing to do with y. Solve two, which has nothing to do with x. This is what we call completely decoupled system. It looks like you have a coupled system with two things, but really each one of them evolve by themselves. They don't interact. Okay, that's the first type. Basically, if you think about it, we can write it to be something like dx over dt equals f x and y before, but really it has nothing to do with y, so it's only fx. So solving them together, solving them separately really doesn't make a difference. Of course, that's doable. Moreover, there's no point of actually putting them as a system. You just solve them separately. Sounds good? Very easy. Of course, in real life, it's never this case. Number two. Okay. Now we have something called partially decoupled system. So it's not completely decoupled, but what you have is something similar to this. Okay. Is this one completely decoupled? The answer is no. The reason is because the derivative of x does have a y in there, so you do have interactions. However, this is called partially decoupled. Simply means this only works for one. For number two, there's no x here. So at least I can treat two separately, not one, but I can treat two separately without considering one. So it's still decoupled, but it only works for the second, not the first. Make sense here? That is still not too bad. Why? Because you can solve two first, pretending you didn't see one. Once you finish solving two, you have a solution of y equals something, right? Then you can put that thing back into here by substituting y of what you just solved from two. Then you can solve one alone. So basically being said, when you say some decouple, basically means that they don't have to be solved together. Okay. If it's completely decoupled, then you can solve each single one separately. You can solve one alone, you can solve two alone. However, if it's partially decoupled, you can still solve two alone for this case. And then when you plug in the result of two, you can then solve one alone. So you can still solve each one alone. This time, the order matter. You cannot solve one first, then two, but you can solve two first, then one. That's basically the case. So solve two. C. E to the negative 4t. Okay. Then substitute into 1. Since you already have the solution, then dx over dt equals 2x plus c e to the negative 4t, which is your y. Okay, and you can go from there. Okay, we're not going to bother to solve this one, but you can see this one can be written into x minus 2x equals c e to the negative 4t. This is exactly integrating factor. Okay, so you can solve by yourself. Sounds good? Okay, that's the rough idea of some special systems we can solve. It's either completely decoupled, which means just solve each one individually, Or it's partially decoupled simply because you can solve one, then plug into the other one, and then solve the other one. Things become more interesting if you have three. Think about it. If you have three, let me just use x prime. This is clearly completely decoupled. You can solve each one individually. Okay. What if I plug an x here? Now, is this one completely decoupled or not? Now, let's talk about it. Number one, z is completely decoupled from other. Actually, not even couple anymore. From x and y. Okay. Number two, x and y are partially decoupled. Which means if you have 1 and 2, you definitely solve 1 first, then 2. Because 2 needs 1. So it's possible when you have 3, you have part of it is completely decoupled, and the rest is partially decoupled. It's possible. Sounds good? Now things become interesting. Can you make some system with 3 things? And they have to be solved in exact order. There's not one of them that you can just toss out and focus on the other 2. Think about this. That will be something look like. I have to solve this first because the second one has x into it. And then I can solve this once I know x, once I know y. Once I know z. Now what's going on? They're fully partial decoupled. Solving either one of them, you have to use the information from the others. Okay, except for the first one. So solve 1. Once you have x, plug it into. You can solve for y. Once you have x and y, plug both into 3. That's something we call a fully partially decoupled. They all depend on each other in a certain order, though. Does everything make sense so far? Okay. So from now on, if you see a big system with a lot of different x, y, z, t, whatever, you have a lot of quantities. The first thing you want to do is actually see if several chunk and several chunk, they're totally independent of each other. Then you can take this big system, break it into 2 subsystems because they don't interact with each other. That's what we call completely decoupled. So maybe you have 10 quantities, 4 of them are together, 6 of them are together. They don't interact at all. That's part 1. Still okay? Part 2, even within the system with 6 variables, maybe they all depend on each other, but if there is an order, that is one is more inclusive than the other, you always tend to solve the easy one first, the one involving the least variable. Then add one more variable, and then add one more variable in this kind of case. In that way, we still have a clear order. We can still actually simplify things when you see a completely messy system. Sounds good? of course, in general, you're not so lucky. You have something that all intertwine each other completely. That is like dx over dt is related to x, y, and z. dy over dt is related to x, y, and z. And dz over dt is related to x and y. So each one involves everybody else. Okay. Then you're not so lucky. You have to actually go through the hardcore steps to solve this. All right. Sound good? Now question. Does this remind you of something you're familiar with? This procedure. Solve one, plug into the second, solve it, plug everything into the third, solve it, plug it back, keep going, keep going, keep going. Something in linear algebra, something look like this. Does it make sense here? How do you solve the system here? You solve this one first, right? Once you have that, you can plug what you just solved into this, and then solve this one. And then you plug the two you just solved, and then solve this one. Okay, it is actually related to the lower triangular system. All right, so this may give you a hint that all these things are actually connected. So that's number 3. We talk about systems, we talk about two values. Now it's time for us to write it in a new way, which is a vector. For example, the thing we did before for predator and prey. Okay, that's how we write it down. XY. A general format. Okay. Now you have done this before. There's nothing to stop you from representing the solution. Instead of separately, you just take a vector, which is called x and y. You take y prime, which is nothing but the derivative of this and the derivative of this. Okay. Then the whole thing can be rewritten into a nice format. Where everything here depends on both x and y, therefore it depends on the vector capital Y, both x and y. Meanwhile, this one has two values, one for top, one for the bottom, so you need to put a vector here. So this becomes a vector function. It takes a n by 1 vector, it produces a n by 1 vector. Okay, in our case just now, Fy equals alpha x minus beta xy negative gamma y plus delta xy. So the whole thing can be rewritten into this format with a particular f defined in this way. Okay. Be right back. Sounds good. That's a nice way of writing stuff. Now let's try to say several things. Number one, the general format, of course, is y prime equals f t y. That's the general format. Autonomous, y prime equals f, no t, just y. Linear, because you already know it's a linear function, so you can write something like this. Finally, linear with a constant. We will call it coefficient. That is going to be y prime equals a times a y, where this a does not change with respect to t. So the a equals something which takes a vector. Okay. Takes a vector and produces another vector. And we're familiar with that. We do know something that takes a vector and produces a vector. That's called a matrix. Okay, so the whole thing can be represented by a matrix. Okay, so that's the point of doing the whole linear algebra thing. When you have a system, you write it into a vector. Then if it's linear, you can represent it by a matrix. For this case, your matrix is actually something depending on t. You can have something like that. Okay, but for constant case, you basically just have a constant in the matrix. That's something we're super familiar with linear algebra. So we can handle that using the knowledge we had before. Make sense to everybody? Okay. A big focus of what we will do is we will focus on a system like this. After that, we don't have time, but later, if you take other classes, they will focus on linear systems with the matrix depending on the time. For everything else, we talk a little bit about how to handle nonlinear cases. In general, they are hard. Sounds good? All right. Now let's talk about the system we just did. Fully or completely decoupled. Remember, we only care about the constant case, so let's just take a look. That's completely decoupled. Take a second look. This is nothing but okay. Remember, this is x, this is y, this is x, this is y. What do you mean by completely decoupled? That means x at x, they're together, and there's nothing involving y in terms of x. So everything else will be 0, except for the x part. What do you mean by decoupled? That means here, my y only depends on my y. There's no x in my y part. So from here, you can see it's very easy to associate what we have here and say that if it's constant linear system, Completely decoupled basically means this is diagonal. That would be the best case ever. You just solve each one, x with x, y with y. X, y don't interact with each other. Sounds good? Okay. What do you mean by partially decoupled? Partially decoupled basically means something like this. We solve one before we solve two, but one is self-contained. Two depends on one, but you can solve one first. That corresponds to a system like this. What is that? That is triangular system. Whenever you have anything triangular, upper triangular or lower triangular, doesn't matter. As long as it's triangular, you go from the least to the most, one after another, one after another, one after another. By the way, the good news about this is it's always n by n, so it's always a square matrix. Sounds good? So for a system like this, everything you had before will work. Echelon form, what does it mean? Linearly independent, what does it mean? What do you mean by null space? What do you mean by column space? What do you mean by linearly independency? Okay, everything. What do you mean by rank? For example, pivoting. Everything will be connected. Sounds good? Think about the third example we gave. What is that? I don't quite remember, but I can write it down. Something like this. Then we say, okay, Z is completely decoupled without X and Y, and X and Y are partially decoupled. Now if you write down the matrix, hold on. That's what you mean. Okay. Finally, the one we just did. Now we can see the system for the second time. This time it's more clear. Number one, this is totally lower triangular. So we should go from the top to the bottoms to solve everything. You solve X first, then Y, then Z. All the information down below needs the information above. That's why it's triangular. Sounds good? Second, if you look at the one on the top, we say Z is completely decoupled. That simply means you can decouple this system into this. On the top, you solve a 2 by 2, lower triangular. Okay. At the bottom, you just solve something which stands alone. Why? Because it's diagonal. Sounds good? From here, you can see it's basically a partition of matrix. To make sure that if you divide the system into multiple parts, the parts don't interact with each other. That's really the meaning of completely decoupling is when you have a matrix, you cut them into several blocks. Okay, it doesn't affect how you solve it because one block does not depend on the other. If you do the same thing here, you will have trouble because these two are not zero. So somehow there are some dependency. As long as they're zero, like here and here, that means they're completely decoupled. Okay, you can do the partition. The second one, you cannot do it. Sounds good? Now if you have a big system, that's the beauty because you can assign this one to one computer, you can assign this one to another computer. They don't even communicate with each other. That's when you start to do parallel computing or distributed computing. You need to decouple them first. All right. Any questions so far? Pretty clear? That's nice. It's a nice format. Now several side topics. Number one, this is great. Diagonal is the best. All right. Then what are the general case? The general case is going to be not diagonal, not even triangular. It will be full of numbers. That's what's in general. Still okay? Easy? Difficult? Then, how do you wish that this is diagonal? You just wish that, right? That means if I give you any matrix, you just wish, this is the diagonal matrix. Of course, it's just blind wish, right? You can't just pray that thing happen. But then, does it remind you of anything in linear algebra? If you even if you see some matrix which is not diagonal, what can you do? You diagonalize it, right? That's the PP inverse. Depending on how your teacher goes, some people go with P inverse DP, whatever. You can diagonalize a system. That means actually after the transformation, you are just solving a diagonal system. That's beautiful. All right. Second, you can solve this one. This one is a decoupled system. All right. My question is there an equilibrium? The answer is yes, it's 0, 0. Okay. Is it a sink or a source? Your solution looks like this. right? That means this is 0, 0. That means if you're a little bit away from 0, 0, what's going to happen? You're going to come back. Why? Because you have e to the negative some t. You let t goes to infinity. This one eventually all go back to 0, right? So this is definitely a sinc. Sounds good? Cool. Do you know how to make a source? Easily. Okay, we don't want complicated ones. We can just do this. We want this one to leave. Okay, you just make it to be positive. Then you have x equal to e to the t, y equals e to the 2t, of course, with a constant. Yeah, I better put it. Okay. Then as long as you're positive, you will go to infinity. Okay, you never come back. That's going to be a source. Make sense here? Okay. Now let's summarize them. The first system is this. The second system is this. This is the sink. This is the source. Now, do you know how to tell if something is a sink or if it's a source? Look at those numbers. Sounds good? If it's negative, e to the negative something, of course it's a sink. Eventually you go back to 0. Question?
Yeah, so if one's positive and one's negative, then be a
Beautiful. What's this? Well, that's going to be what do you think? That's a node, right? Okay, so beautiful. If it's all negative, that means it actually goes to here from all direction. Same thing with calculus 3, right? Maybe in one direction you have a limit, maybe in another direction you have a totally different behavior. Okay, a sink, you need everybody to actually all come together. For something like that, it's very possible that you have a solution looking like that way, which don't come to your equilibrium, so it's not a sink. Okay, it's not a source either, it's part. So let's do note. Make sense to everybody? Okay, so sink or source, you just look at all those numbers. That's it. Okay. Question. What are these numbers called? Especially, this is nice because you can look at the number. For in general, you cannot look at the number, right? This cannot be right because you have to make sure these two are 0 first. You need to make a diagonal system first. So what are these numbers for a general thing? That is called the eigenvalue. You can easily observe that because the eigenvalues of the diagonal is easily the diagonal elements. So you can see the eigenvalue right away. But if there's no eigenvalue, no direct access to eigenvalue for any matrix because it's not diagonalized yet, well, you can find the eigenvalue yourself. We did the whole section, a whole chapter in linear algebra to do that. Sounds good? Okay, that's beautiful. Or in another way, you can think about this. Okay, that's the third thing. What I just wrote down is nice. You look at the matrix, you basically just look at the eigenvalues. You will know if it's a sink, it's a source, or it's neither. Okay, moreover, do you realize what I just wrote down with something look like this? where A is a matrix, right? Can you solve this thing? If you just pretend it's one dimension, or let's just say AY. What's the solution for this? E to the TA. That's for one dimension. What now? E to the TA. Of course. The only difference is this time you do E to the TA and A is a matrix. You just never seen something like this before. It's like, what do you mean by E to the 1001? What do you mean by that? Make sense so far? Okay, once you can figure that out, you should be able to compute it then. It's just like, what do you mean by E to the matrix here? Okay, let's think about what we know about matrix. We know how to do A. We know how to do A plus B. That's still a matrix, yeah. We do know A times B. Still okay? Anything other than that, we don't know how to do. For example, what do you mean by sin A? What do you mean by, I don't know, square root of A? Things like that. We don't know how to do it. Make sense so far? So the knowledge stops here. We only know how to do multiplication and plus. Now question, if you know A times B, of course you know A times A, which is A squared. You can compute the power of A easily, right? Right? Cool. Then the question becomes, can this one be represented as a power of A? If yes, then done. Because we know how to do power of A. Okay. Question, can this be represented by a power of X? More precisely, can this be represented by a polynomial-ish thing, which has a name, which goes forever, which is called Taylor polynomial. That whole thing is connected. So e to the x, what is e to the x? E to the x is 1 plus x squared over plus x cubed over. That's called Taylor expansion. Then what about e to the TA? That's okay. What do you need to know? Well, you just need to know how to compute a squared, which is a times a, which we do. Therefore, we do have the capacity to compute this. We can actually approximate it with a computer. The computer can do 100 terms and say that's an approximation. That's certainly doable. Sounds good? Okay, so that's actually the ultimate way of how to solve a system like this. You basically just solve e to the TA. E to the TA is nothing but just this one times a lot powers together. By the way, if you're looking for sin A, square root of A, okay, which you don't know how to do, but just think about this. You do know the Taylor expansion of sin x as square root of x, right? After that, it's just the power of A. So you can basically do any functions as long as you have the Taylor polynomial. Sounds good? Okay, that's the whole thing about how to integrate linear algebra into this knowledge we just did. Coupled, decoupled. In real life, usually we just handle things like this. Linear with constant. If it's linear, but it's not a constant, it's changing with time, with the computer, we can actually change it to be T0, T1, T2. Okay, if you want to study what's going to happen to this from 0 to 1. Okay, what's going to happen is we're going to do 0, 0.01, 0.02, just as the way we did Euler's method. We have a lot of time steps. Still okay? Then on each time step, we just assume A is a constant. Because we just plug in a T, you stay constant for just period of time. Sounds good? So this generates to this. And to finish this, you just need to take the limit. To have infinite many, and of course, points, but of course, for computers, you stop somewhere. Okay. Now here comes, guys. What if it's nonlinear? For example, it's like y squared. Technically, it's not right. You know, you cannot square a vector, but more or less. What do? You do linearization. So again, it becomes linear, but again, it only works for a small interval. But then again, using Euler's method, you just track all of them. You have 1,000 steps for on each one is a linear, even though the whole thing was not linear. Sounds good? Okay, so actually our focus will be on here for all the course. But actually, once you have that, you can discretize anything with respect to t. Assuming it's a constant, you can handle that case by taking the limit. After that, even if you have something nonlinear, locally discretize it, you can handle with that. So it's almost the same as if you have some function. Technically, you don't have f prime x, but instead you can always do fx plus h minus fx divided by h. Well, more or less, this one's not accurate until h goes to 0, but it works if you just give it 1,000 steps. It's working. Okay, it's the same idea here. All right, that's everything we have for 2.4. Now let's go to 2.5. Yeah, that's my thing. I don't know what this book is doing. Yeah, they just jump from one place to another. Either way, Euler's method. Before, for Euler's method, we first have the vector field, and then we start from here. We go this much, calculate the vector field again. We go this much, calculate it. Okay. In this way, we trace the whole thing, the trajectory of the whole thing in the ty plane. So that's the solution. Which works just fine. Okay, and if you want it to be accurate, you just take smaller vectors, do more steps. Sounds good. All right. So this time, we want to still do the same thing, except this is t, this is x, this is t, this is y. Except every time you are trying to calculate the vector here, which is the derivative, which is dx over dt, dy over dt. Okay, you just need to take into consideration this one also depending on the current y value. Okay, so you do them together. That's basically the difference. Or actually, there's no difference. So. Okay. Another way, however, to visualize it is actually you're just doing this thing in the phase plane. Every single point, you are going to have a dx and dy. You just go that far. Okay. Every time you do it, So tracking both in the parametric format is the same as tracking the thing in the curve. They're actually the same. So yeah, I think the method is pretty straightforward. All right. In one dimension, y, t plus 1. Let's do n plus 1. Equals yn plus a delta t times f yn tn. In 2D or 3D or whatever, so just like a system. Y, n plus 1, which is a vector, by the way. So yeah, let's just write this down first. Or more precisely, if it's 2-dimension, f, g. All right, let's stop here. Next time I will do the manual example for 2 steps. So you see the method, and then we try to do it in the computer. Then we try to show how the computer is going to fail. For systems, it's very easy for the computer to fail because you have 2 things interacting each other. The error just accumulates like crazy. Cool. That's all for today.